All right, so let's go back to that other first order condition where we took the derivative with respect to beta hat 1. We had this extra x1i at the front. Beta hat 0, beta hat 1, x1i. And this was our first order condition. So what we're going to do now is, well, we're going to plug in that beta hat 0 equals y bar minus beta hat 1 x1 bar. That's what we just solved for. And what we're trying to do otherwise is to isolate, oops, not beta hat 0. We're just trying to isolate beta hat 1. So we're going to plug it in, what we got for beta hat 0, and then we're going to isolate for beta hat 1. So the first thing we can do is think about, well, let's just plug it in first. It'll be easier to see. And that should turn into a plus, minus is a plus, minus beta hat 1, x1i equals 0. Right, so this was a minus here, but we're subtracting beta hat 0, so it turned into a plus right there. Okay, so like I was trying to say above, but maybe got a bit messy, we're trying to isolate for this beta hat 1. That's what we're trying to solve for now. So notice it's a common factor of these last two terms, and maybe we could start to think about kind of dividing this between terms that have beta hat 1 in it and terms that don't. Okay, so let's just do that. So the first sum we're going to have is these first couple terms. So let's just leave those together since they don't have a beta hat 1 involved. And then we're going to think about another sum. So let's common factor this beta hat 1 out. We still have this being multiplied in, so x1i. Then we have x1 bar minus x1i equals 0. So between these two lines, we're just kind of dividing the sum right here. We're kind of keeping everything there together, and we're kind of keeping the terms that have this beta 1 hat common factor. And we can think about now moving this to the other side, right? Because then we can think about actually isolating this beta hat 1. So we're going to move this to the other side, and when we do that, we're just going to flip these two x's. So now it's going to become x1i minus x1 bar, right? Because that's what we're doing as we move it over. So instead of changing this to a minus, as we bring it over here, we're actually just going to flip this, what's in the brackets, if that makes sense. And then equals beta hat 1, the sum x1i minus x1 bar. And we're almost there. Now we just need to isolate for this. So I'm just going to move it to the other side. Beta hat 1 equals the sum. I'm just going to write it a little bit differently here. Forgot this. But oftentimes, so that's perfectly fine. This is one way of expressing the slope parameter, or the slope estimator for our OLS. But a lot of times you're going to see it written a little bit differently, and mathematically it's equivalent. It might seem a little bit crazy, but it is. So these are mathematically the same thing, these two things. Might seem crazy, you can do the math. Basically what it's saying is that x1i minus x bar times x1i is the same as x1i minus x bar squared, and the same for the numerator. You can You can try that mathematically and you'll see they're the same, just using rules of sums. All right, so now we've solved for our least squares estimators for simple regression. We have beta at 0, so what our estimator for the intercept for this, for the regressions are going to be, is we're taking the sample mean and we're subtracting the slope parameter times the sample average for x1. So the sample average for y minus whatever this estimator is, we're going to write down below, times the sample average for x1. And again, we solved just for this. I'm going to write it in that other way that, that we were talking about. X1i minus x bar, I guess we're putting a 1 there, and then the same thing down here squared. So these are our estimators. So these are the rules that we're going to apply to our sample to come up with parameter estimates for the intercept and the slope.